Assalamu alaikum everyone. So this is the third part of our lecture 11, which is the nonlinear regression lecture. And for the third part, we'll learn about the growth model, the logarithmic model, and the power model in this lecture. Okay, so let's fast forward to that slide. Okay, so the growth model. So the growth model looks something like this: y equals to a divided by 1 plus b e to the power minus cx. Okay, so if you look at an example over here, this is the graph of y equals to 10 divided by 1 plus 2 e to the power minus 0.7x. Okay, so for those of you who took the machine learning course, I think you guys are familiar with this type of curve, right? It looks like the sigmoid function that we used in our logistic regression, right? So the growth model looks something like that, and the difference between the growth model and the saturated growth model is in this region over here, which is that the normal growth model has a positive or a non-zero y-intercept. Okay, so as we go towards zero, or when x is equals to zero, which means we start at the origin, the value of y is what? A divided by 1 plus b, which we call our y-intercept, right? And as x goes towards infinity, and as x goes towards infinity, we say that the value of y gets capped at a, right? So the value of y is somewhere over here. It gets capped at a value, say a. So for this equation over here, the value of a is 10, right? So we can see that at the value 10, the value of y gets capped, right? So now our next task is to uh, find out the errors, right? So let's say we have some data points given over here, something like this. Say some random data points. Okay, so let's pick one data point and try to find out its error. So let's say this point over here, the actual value is somewhere over here for the data point, but the predicted value is what? Somewhere over here, right? So this disparity over here, we call that our error, right? So this thing over here is our EI. So the EI can be something like this. So yi equals to, yi minus a divided by 1 plus b e to the power minus cxi, right? Because the actual value is yi and the predicted value is a divided by 1 plus b e to the power minus 6xi, right? Now the sum of the square of the residual errors looks something like this, right? So this whole error over here, whole square, and the sum of all the values from 1 to n, right? So let's try to derive the parameters. So let's go to our bamboo paper and see how the derivation works. Okay, so recall that our growth model equation, or the equation for our growth model regression curve, looks something like this, right? Y equals to a divided by 1 plus b e to the power minus cx, right? So, and the sum of the square of the residuals looks something like this. So SR is equals to the summation over all i's yi minus a divided by 1 plus b e to the power minus cxi, right? And whole square. Uh, okay, so we know that in order to find the critical point, we have to take the partial derivative of the SR value with respect to the parameters as 0, right? So one of the critical points will for sure be the minima, right? And the minima will find the optimal value of these parameters, right? The value of the parameters for which we get the best fit curve, right? So let's do that. So del SR by del A equals 0, right? This is the first parameter for a. So if you perform the differentiation over here, it looks something like this, pretty simple. 2 times for all I yi minus, so the bracketed term will remain as it is, 1 plus b e to the power minus cxi times, so that 2 comes to the front, and we are differentiating with respect to a, right? So a is over here, so this is our term of interest. So we'll just take the constant part, which is the denominator over here, out. So we'll get something like minus 1 divided by 1 plus b e to the power minus cxi, right, equals to 0. So we can further simplify this. So this it in and of itself is okay, but we can further simplify this in order to match with the equation given on the slide. So let's do that. So 2 times I from 1 to n. Let's take this denominator. Let's multiply these two terms. We get something like what? Uh, so this minus becomes plus, this minus and this minus becomes plus. So a plus 1, a divided by 1 plus b e to the power minus cxi whole square, right? Because this denominator and this denominator multiplies, they are the same thing. So it becomes square, right? And we have, so this yi, it initially had a positive in front of it, right? But after multiplying with this minus, it becomes minus. So yi divided by, and this whole denominator over here, 1 plus b e to the power minus cxi. Okay, fine. So this whole thing is equals to 0. And now let's proceed to the next step, which is what? To join these two terms, right? So we have a denominator, common denominator. So we will do some basic algebra. So the whole denominator looks something like what? 1 plus b e to the power minus cxi whole square. And since this one had a single instance of 1 plus b to the power minus cx1, we have to multiply with yi, this term over here, right? So 1 plus b e to the power minus cxi. Okay, so now that we have this, what can we do? Okay, so e to the power minus cxi can be written as what? 1 divided by e to the power cxi, right? So let's do that. Let's write it as something like this. So 2 times I from 1 to n, we have a minus yi times, so if we take the denominator, we should get some, if we take this thing to the denominator, we should get something like this, right? E cxi. And the same thing can be done at the denominator as well. So these things becomes 1 plus b divided by e to the power cxi whole square, right? Equal to 0. Now let's proceed with the symbolic manipulation, which is 1 to n. Now what we can do is we can take this denominator and bring it to the numerator, or basically expand this, right? So we can do something like this. So summation from I equals to 1 to n, uh, let's say a minus, a will remain as it is, yi will remain as it is. We can say what? E to the power cxi plus b divided by e to the power cxi, this whole thing over here. And at the denominator we can do the same thing, which is e to the power cxi plus b divided by e to the power cxi, right? And since we have a whole square over here, there will be a whole square over here also. So this whole thing is equal to 0, right? Now what we can do is we can so we'll expand the numerator further, and we'll see that we'll be able to cancel out the e to the power cxi's. Okay, let's see how we can do that. So let's expand it further. So we get something like so we take this e to the power cxi and take it to the top. We get something like what? A e to the power cxi minus yi times e to the power cxi plus b divided by e to the power cxi. So this is the whole numerator part, and the denominator part we do the same thing. So instead of doing the same thing, we can just square it. So we get something like what? E to the power cxi plus b whole square. So we separate out the numerator and the denominator. We get what? So e to the power cxi square is e to the power 2 cxi, right? To the power 2 cxi. So now that we have this whole thing is equal to 0, right? Okay, so clearly we can see that the e to the power cxi term and e to the power 2 cxi term can cancel one instance of this term over here. So we get something like e to the power cxi, right? So now that we have this, our life becomes pretty simple. So what we can do is we can take this e to the power cxi and take it to the top, right? You can flip it around. So we can get something like uh, 2 times summation of I from 1 to n. Mm, let's take it to the top. So we get something like, okay, so what we can do is we can take the 2 inside also, right? Because it's a linear operation. So we get 2 times e to the power cxi. So this e to the power cxi is the e to the power cxi we see at the denominator here, right? We are just flipping it and taking it to the top. Okay. So this thing over here times this whole numerator, we get a times e to the power cxi minus yi times e to the power cxi plus b. This whole thing will be multiplied by what? 2 times e to the power cxi. Okay, and at the denominator we have remaining e to the power cxi plus b whole square. Fine. So this whole thing is a what? It's a trivariate function, right? So we can say that the function looks something like this. So a comma b comma c. This function changes with 3 changeable parameters, right? So for solving such a nonlinear function, we need a what? A root finding algorithm, right? Like Newton-Raphson and bisection and whatnot, right? So for the sake of completion, let me write the equation for the next two parameters as well. So for DSR divided by DSR divided by for delta SR delta B equal to 0, we end up with an equation that looks something like what? Uh, Summation of I from 1 to n to a e to the power cxi times byi plus e to the power cxi times yi minus a. This whole thing at the numerator, and at the denominator we have e to the power cxi plus b whole cube. Okay, this whole thing is equal to 0. And for the third parameter, which is c, so del sr with respect to c, so del sr by del c, we take it as 0, and we get a corresponding equation which looks something like this, a nonlinear equation, mind it. So summation from I equals to 1 to n we get something like 2a bxi e to the power cxi times byi plus e to the power cxi times yi minus a. This whole thing at the numerator, and at the denominator we have e to the power cxi plus b whole cube. Okay, so this whole thing is equals to 0. So what we have over here is three trivariate equations, three trivariate nonlinear equations. So let's mark them. So let's say we have this thing as our equation 1. So this is our equation 1. So I have left out the derivations for these two due to their lengthiness. So you can trust me that we end up with these two equations. You can mark that thing as our equation 2 and this thing as our equation 3. So if you look closely, all of these trivariate, so the name, they are trivariate functions, right? Because they change with respect to a, b and c, three parameters, right? So we have three unknowns and three equations, right? So if we solve these three equations, we should be able to end up with the three unknowns, right? So in order to solve these three nonlinear simultaneously nonlinear equations, we need a root finding algorithm, okay, which will help us to find the value of f a comma b comma c equals to 0. So the points, the values of a, b, and c for which these trivariate functions yield the value 0. Okay, so we can use Newton-Raphson bisection and whatnot. Okay, and there are many root finding algorithms. So in the slide, they tell us to use the Newton-Raphson method. Okay, now that we have come back to the slide, you can see over here that we can use the Newton-Raphson method, okay, to solve these three simultaneous nonlinear equations, and we can obtain the we can converge to a good value of the parameters a, b, and c after a certain number of iterations. Okay, now we'll see how this can be done in our upcoming example. So let's do that. So we know that the growth model regression curve can be used to model the height of a child. Okay, so when the child is born, he's say his height is 20 inches, and at the age of 18 he has let's say that uh, his height is 70 inches. Okay, and there are a total of 1, 2, 3, 4, 5, 6 data points of ages and their respective height measurements. Okay, so the question asks us to predict the height of the child when he becomes 30 years old. Okay, so we'll use the growth model, which is h equals to a divided by 1 plus b to the power minus ct. So we are just replacing y with h and x with t. Okay, so our uh, regressor variable is what, t, and our response variable is h, which is the height of the child. Okay, okay, let's see how it can be done. So since this is our regression growth model, we have already derived these three equations in our previous segment, right? So using the so our job is now to solve these three equations to find out the three unknowns a, b, and c. Okay, so in order to start our root finding algorithm, we need a starting guess, right? So let's say we are using the Newton-Raphson method, and we need a starting guess, right? So we need three starting guesses in this case because we are trying to find out three values, right? Three parameters at the root, right? So one obvious way to come up with the starting guesses is to use the given data points. Okay, so let's say we take three random data points, 0, 20, 12, 60, and 1870, and use them and plug them into the to the given growth model. Okay, so using this growth model equation, we just plug in the values of h, t, and h. So 0, 20, 12, 60, and 1870, and we solve these three equations. So there are three equations, and we have three unknowns, right? A, b, and c. If we solve them, we get something like what? A equals to 7.55 times 10 to the power 1, b equals to 2.77 something, 3 c is equals to 1.977 something into 10 to the power minus 1. Okay, Now these three values of the respective parameters, we can take them as our initial guesses. Okay, so now that we have our initial guesses, we can initiate our Newton-Raphson method. So the problem says that, okay, after some number of iterations, we converge to these three values. Okay, so for A we get 7.43 times 10 to the power 1, for B we get 2.82 something, and for C we get 2.17 times 10 to the power minus 1. Okay, so we just plug them into into our saturation growth model equation. We get something like this. So H equals to this whole value of A at the top divided by 1 plus this whole value of B times e to the power minus this whole value of C times T. Okay, so if we plug in our say the value of T, so the question asks us to find the height of the child at 30 years old. Okay, when his age is 30 years. So we plug in the value of T as 30, we get a value what, 74 inches, right? So we can say that, okay, using our growth model, we can predict that at 30 years of age, the child will be 74 inches tall. Okay, fine. So now that we have learned the original growth model or the core growth model, we'll talk about the logistic version or the saturated version of the growth model. Okay, so in the logistic growth model, the equation is y equals to ax by b plus x. So we touched upon this equation a bit in our overview slide at the beginning of the lecture. So we'll talk about this in depth. So what we have seen from our previous growth model is that we had to use a root finding algorithm and conduct so many iterations to come up with the parameter values, right, or the a and b and c values. So we have to do the same thing in the case of the growth model, in case of the saturated or the logistic growth model as well. So how can we sidestep that overhead? Okay, how can we avoid that hassle, so to say? So we have learned, right? So in order to avoid the hassle of this computational overhead, we can basically uh, transform our data, right? So we can transform the given data or linearize the data, right? So we'll see how we can do that for the growth model. But before that, let's see how the behavior of the logistic growth model is. So for x equals to 0, so at the origin, we can for sure say that the curve passes through the origin. Okay, so there will be no y-intercept, or the y-intercept will be 0. So for x equals to 0, we get y equals to 0. Now as x tends to infinity, y gets capped at a. Okay, so the same as the original growth model, we can say the logistic growth model also gets capped at the value a. Now it may be a bit unintuitive to see from this equation how the value of y gets capped at a. So we'll just perform some limit operations and see how it can be done. Okay. Okay, so we are back to our bamboo paper. So recall that the equation for the logistic growth model was what? Y equals to ax divided by b plus x, right? So let's say we are trying to find out the value of this equation when x is infinitesimally large, right? So we do what? Limit x tends to infinity ax by b plus x, right? So let's factor out a over here very simply from the numerator. So let's write it as a times x. Let's write it a bit clearly. A times x divided by b plus x, right? So we'll do this for our convenience. So limit x tends to infinity. So if we plug in the value of infinity over here and here, we can see that it becomes something like what, infinity by infinity, right? So we can apply the L'Hopital rule here, right? If you guys recall from your HSC calculus chapter, we use the L'Hopital rule in our limit problems, right? So we can say that, okay, so this becomes a what, infinity by infinity case of the L'Hopital rule, right? So we can differentiate the numerator and the denominator, and we get what, something like this. So ddx of x is what, 1 divided by ddx of b plus x is what, 0 plus, so for x we get 1, right? So we can say that, okay, limit a times 1 divided by 1, which is 1, so which is basically a, right? So as x tends to infinity, we can say y becomes a, right? So y is asymptotically gets what, parallel to the value of y gets asymptotically close to a, right? Okay. Okay, so now that we are back on the slide, so what was our initial goal? So our goal was to what? To avoid the hassle of calculating the parameter values using just by solving the nonlinear simultaneous nonlinear equations, right? So how can we do that? We can do that by transforming the data, right? So let's see how we can do that for this logistic version of the growth model. So let's go back to our bamboo paper and try to derive them. Okay. Okay, so our saturated or our logistic version of the growth model looks something like this, right? So let's try to linearize it. So what we can do is we can simply perform a good algebraic hack, which is we can reverse it on its head. Okay, so we basically write y as 1 by y, or we flip it around. So we flip around both sides, we get what, b plus x divided by ax. Okay, so 1 by y equals to b plus x divided by ax, which is basically the reverse version of the initial growth model. Okay, initial logistic version of the growth model. So let's try to simplify it further or write it a bit differently. So 1 by y becomes what? B divided by a plus x divided by a plus x. Okay, so we can write it even more simply, which is uh, b by a times 1 by x. So this b by a and 1 by x get separated, and plus, so this x and this x cancels each other out. We we get left with 1 by a, right? Now that we have this equation over here, I guess you guys can see that we can express this thing as a linear equation, right? As an equation of a straight line, right? So let's denote 1 by y as z. Let's denote say b by a as what, a1. So in order to maintain the similarity with our linear regression equation, so let's write 1 by x as what, w, and let's write 1 by a as something like a naught. Okay, so this whole thing becomes what, z equals a naught plus a1 w, right? So this is clearly the equation for the linear regression model, right? Now if we transform the data maintaining these relationships, we can end up with a what, linear regression model, right? So using the formula that we have derived for the linear regression model, we can find out the values of what, a naught and a1, right? So let's say we applied those formulas and found out the values of a naught and a1 respectively. Now we know that a naught is equals to what, 1 by a, right? Because we have already drawn the parallel over here. So a naught is equals to 1 by a. So after we find the value of the parameter a naught for the transformed version of the model, we can find the value of the parameter a for the original version of the model, right? For the original version of the logistic growth model. So we can write what, a equals to 1 by a naught, right? So this is one value of the parameters. So for b, what can we do for b? So we know that a1 equals b by a, right? So we can write b by a as what, b times 1 by a, right? So we can also rewrite b times 1 by a as what, b times 1 by a was what, a naught, right? So b times a naught, so we can say that okay, a1 is equals to b times a naught. Or we can write um, what, so we need to find the value of b, right? So we can write b as a1 divided by a naught. So after we find the value of a naught and a1, we just divide the value of a1 by a naught and we get the value of b, right? So now that we have found the value of a and b, we can plug it into our original logistic growth model equation, and we'll find the what the best fit or the suboptimal, right? We know that after performing data transformation, what we end up with is a suboptimal regression model, right? Not the optimal one. So we'll end up with somewhat good regression model, or a logistic growth curve regression model, okay, which is y equals to ax by b plus x, where the value of a and b were found after performing the data transformations, okay. So now that we know how to linearize the growth model, logistic growth model, let's see how we can apply it to an example, okay. Okay, so we are back to our presentation. So let's say you have an example where a set of x values and a set of y values are a set of x values and a set of y values are given for a particular example, and you are asked to fit the logistic version of the growth model through the data, okay, in order to form a regression curve. So what you can do is, okay, simply you can find the corresponding zi and the wi values by transforming the data according to these two relationships. So what you'll end up with is the wi values and zi values, right? Now we can form a table just like before in order to find these values that we'll be using in the formula for the linear regression parameters a1 and a0. So after we find the wi and zi values for all the data points, we can basically use our calculator to find out the summation values, right? Summation of wi zi, the summation of wi times the summation of zi, and the wi square summation and the wi whole square summations, right? So after we find the value of a1 using those found values, we can plug the value of a1 over here and use this formula to find the a0 value, right? So after we find the a0 and the a1 value, we can use the relationships that we have just derived in our bamboo paper. We can find the value of what the a and b parameters, right, for the original logistic growth model curve, right? Then after we plug in the value of a and b in the curve over here, we'll find our corresponding suboptimal, mind it, suboptimal logistic version of the growth model regression curve, okay. So okay, here is a mini quiz for you. So what did we do just now? So we basically linearized the logistic version of the growth model, right, which looks something like this: ax by b plus x, right? So we linearize this version of the growth model. But what about the original version of the growth model? Y equals to a divided by 1 plus b e to the power minus cx. Okay. So is there any way to linearize this growth model? If so, how? And if not, why? Okay. So just write your answer in the comment section of the post that I'll be giving, where I'll be uploading the materials in the video. Okay. Uh, okay, so if you can answer it correctly, of course, you'll get some bonus marks. Okay, okay, let's move on. Okay, now we'll talk about the uh, logarithmic model. Okay, so the logarithmic model is pretty simple. So it looks something like this: y equals to beta naught plus beta 1 ln x. Okay, where beta naught and beta 1 are the corresponding parameters of the model. So just like a and b was for the logistic version of the growth model. So we have b naught and beta naught and beta 1 as the parameters. Okay. So what we can do is, so since we have this as our logarithmic model, so I have left the derivation of the parameters to you as an exercise. So, but however, I'll just give you a little bit of hint. So just to taste the flavor of how this starts to become just another task of solving simultaneous nonlinear equations. Okay, so we'll have to invoke some sort of root finding algorithm to find the value of beta naught and beta 1 in order to fit the logarithmic model curve. Okay, and we'll segue that into uh, finding the corresponding linearized version of the model, of the data transform version of the model. Okay, so we'll try to fit a linear regression curve instead of a logarithmic model curve. So let's see how we can do that. Let's go back to our bamboo paper. Okay, so recall that our logarithmic model would look something like what? Y equals b naught plus, sorry, beta naught plus beta 1 times ln of x, right? So if we let me change the color a bit. Okay, so if we want to find the optimal values of the parameters, we needed to find the critical points, right? The value of the parameter values at which the sum of the square of the residuals yielded a minimum value, right? So let's try to write the sum of the square of the residuals at first. So it should look something like this, right? From 1 to n, we should get yi, which is the true value, minus our predicted value, it is beta naught, minus, so this minus in front of this plus yields this minus. So we have beta 1 times ln of x sub I, right, or xi. So, and we'll have a whole square because it's the square of the sum of the residuals, right? So, okay, so sum of the square of the residuals, sorry. Okay, so now that we have this, so we'll perform the partial differentiation, which is differentiating the SR with respect to, let's say at first we'll do it with respect to beta naught. So this will of course be 0. So we can write it as something like this, right? So 2 times summation of I equals to 1 to n yi minus beta naught, so the bracketed term will remain as it is, minus beta 1 times ln x of I times, so this whole square comes to the front, so which is why this 2 manifests. So what do we have? So we are differentiating with respect to beta naught, right? So beta naught is over here, implicitly multiplied with the minus 1, right? So we'll just bring out this minus 1 and set it as 0. Okay, fine. So now that we have this, so we can just multiply, so we can basically cut this, cancel these 2 and minus 1 out, because we are, it's basically the same as dividing both sides by minus 2, right? So what we end up with is something like this. So from I equals to 1 to n, we have yi minus beta naught minus beta 1 ln x sub I equals 0, right? So let's mark it as our, let's mark this as our what, equation 1, and let's do the same thing for uh, beta 1. Okay, so we will differentiate SR, delta SR divided by delta beta 1, so the second parameter, right? So this will of course be 0. So let's differentiate it. We should get something like what, so 2, that 2 will come to the front, and we have I from 1 to n yi, the bracketed term will remain as it is, right? Yi minus beta naught minus beta 1 times ln of x sub I. Okay, so we are differentiating with respect to beta 1, right? So beta 1 is over here. So what we can do is we can just take out the minus ln xi, and we are ready to go, right? So minus ln xi equals 0, right? So this thing, so without simplifying it further, we can see, right? So this whole thing is another non-linear bivariate equation, right? So both of these equations have two tweakable parameters, right? So f of beta naught comma beta 1 equals 0. So this is also another non-linear bivariate equation, beta naught comma, so let's write this a bit clearly, it's a horrendous beta. So beta naught beta 1 equal to 0, right? So in order to solve or to find the values of beta naught and beta 1, so you have two unknowns, right? So if we solve these two equations, these two simultaneous nonlinear equations, we should what, end up with the optimal values of beta naught and beta 1. But we have seen that in order to solve these simultaneous nonlinear equations, we have to invoke what, our root finding algorithms, right? And they take a whole lot of iterations to converge to a good estimate, right? So that's a lot of computational overhead. So you want to avoid that hassle, right? So in order to avoid the hassle, what do? We linearize, right? We just transform our data, right? So let's see how we can do that for the logarithmic model, which is y equals to b naught plus b1 beta naught plus beta 1 times ln x. So the idea is pretty simple. We just convert ln x to another variable, right? So we write it as something like this. So instead of y, let's write it as z for the sake of closure. So let's write it as z. Let's write the whole equation at first. So initially we have what? Y equals beta naught plus beta 1 ln x, right? So let's say, okay, let's convert, say, let's denote this y as z. Let's denote this beta naught as what? A naught. Let's denote this beta 1 as a1. This is an a naught. Okay, and let's denote this ln of x as w, right? So what we end up with is z equals a naught plus a1 w. So what we are basically doing is we are saying that okay, our regressor variable will be ln of x instead of x, okay, and our response variable, which is the variable that changes with respect to the independent variable, we also call it the dependent variable, right? Which is y. So okay, the y will remain just as it is. We'll just denote it using z now. Okay, fine. So now that we have our corresponding linear regression model, we can use our derived formulas that we derived back in lecture 10, I think, yeah, in lecture 10. So we'll use those two formulas to find the values of a naught and a1. Okay, let's say we have found these two values. So after we end up with the values of a naught and a1, we can simply backtrack and find the corresponding values of beta naught and beta 1, right? So we know that a naught is equals to beta naught and a1 is equals to beta 1. So whatever values we end up with for a naught and a1, we can write the exact same values as the answers for beta naught and beta 1 respectively, right? So just one additional thing that we have to do is to convert the x values that we have to the corresponding w values, okay, just by performing natural logarithm on them. Fine. So now that we know how to linearize our logarithmic regression model, we'll just study a simple example and see how it works. Okay, let's go back to the slide. Okay, okay, so now we'll use our logarithmic regression model to model the regression curve of a battery, okay, on a fuel cell. So the fuel cell is made using sodium borohydride, and we are given the voltage values or the over potential values denoted by eta over here, and the current values, okay, or the current values in amperes. So we have the corresponding current values of the battery. Okay, so these are the voltage values and these are the current values. Okay, so the model or the logarithmic model is eta equals a plus b times ln of I, okay, where I is the current value and eta is the voltage values. Okay, so our target is to find the values of a and b. So in electronic for this problem over here, the value of 8 basically signifies the electrochemical kinetics parameters of the chemical borohydride, which is used in the electrode of this battery. And the beta, what does the beta signify? Sorry, what does the b signify? It is not written over here. We'll find it anyways. Okay, so let's proceed to see how we can solve the example. Okay, so our first task is to convert the data, right? So transform the data. So we are given the I values, we have to what convert it to the corresponding x values, okay, because we have uh, supposed that, okay, we have taken our linear regression model as y equals to a plus bx. Okay, so recall that our parameter values remain the same exact as it is. So when we derive the value of a naught and a1, we find out the corresponding value of beta naught and beta 1, right? So it's the same as not changing the denomination at all, right? So we can basically keep the a and b values as it is. So that's what they have done over here. Okay, so they just changed the value of ln I to x. So now that we have the value of I, so don't confuse the value of I over here and the value of I over here in this table. The value of I over here corresponds to the current values, right, which is given in the unit of amperes, and this I over here denotes the index, okay, or the indices of the given data points. So now we are given the value of the uh, I, or the current values, and the voltage values, right? So our first task is to convert the I values to the corresponding xi values. So what we can do is we can perform natural logarithm on this whole column over here. We end up with this whole column over here, right? Now after we find the corresponding x values, we just need to find the corresponding x square values, which is this column over here, and the x times y values, right? So which we need for this whole summation thing over here. If we find all of these columns over here, you can sum them up, and this last row basically signifies the sum of the uh, preceding rows, okay? So we can use the values we obtained in the last row and plug them into our linear regression parameter formula, which is the formula for finding the a1 parameter, which is b in this case. So if you plug them in over here, we'll get the b value, and after we find the b value, you can plug the b value over here and use the y bar and the x bar, which is the average value of y and the average value of x, to find the second parameter, which is our a naught parameter, or the a parameter in this example. In this specific example, we'll find the a value as well, okay? So we just from the last row, we'll just record these summations over here because we'll need them in this formula over here. So after we plug the uh, values of the summations that we have obtained in the last row of the table in this formula, we get something like what? B equals to minus 1.36 something, right? And A equals what? Minus 8.599 something, right? So after we find the value of A and B, we can simply plug them into our original equation, which is eta equals A plus B ln I. So we get what? Eta equals minus 8.599 minus 1.36 something times ln I, right? So if you plot this graph in Desmos, we should get something like this. So understand that the scales are different, okay? Along the x-axis, we are taking a very minuscule scale, okay? So some a value times 10 to the power 3, whereas in the y scale, or the vertical axis, in the y-axis, our scale is a bit larger, okay? So from minus zero point 0.1 to minus zero point 0.3. So it basically roughly looks like a straight line, okay? Straight regressor line passing through all the given data points, okay? So now we know how to transform our given data to a linear regression, to a corresponding linear regression model, and backtrack it to find the corresponding logarithmic model, right? And just like before, whatever we end up, whatever values of the parameters we end up, will give us a what? A suboptimal value of the parameters. Okay, it's not optimal. Uh, what the parameter values that we would have gotten without transforming the data would have been optimal. Okay, fine. So let's move on to the power model. Now that we have completed the logarithmic model, the power model is very easy compared to that. So the power model looks something like this: y equals a times x to the power b, where a and b are the parameters of the model. Okay. So just like before, I'll leave the derivation as an exercise to you guys. So I'll just provide a brief hint as to how the uh, derivations might look. So let's go to our bamboo paper and see. Okay, now that we are back to our bamboo paper, let's analyze the power model. So recall that the formula, or the equation for the power model look what? Something like y equals a times x to the power b, right? So our sum of the square of the residuals, so SR, will look something like this. So from I equals to 1 to n, should get what? The true value yi minus the predicted value a times x sub I to the power b whole square, right? So let's try to derive the optimal values of the parameters a and b. So for that, we need to differentiate, or partially differentiate, SR with respect to, let's say, the first parameter a, okay? So we take this thing as 0, so del SR by del a equals 0. So if we differentiate it, it looks something like this, right? So the 2 will come to the front. We have y from 1 to n, yi minus a times x sub I to the power b times what? So since we are differentiating with respect to a is present in this term over here. So it is implicitly multiplied with minus 1. So we have minus what? X sub I to the power b, okay, equals 0. Okay, so without simplifying it further, we can see, right, that the equation that we have ended up with is a non-linear equation, right? So let's take it as our first equation, and let's head back and see what we can do in the case of pp, okay, or the second parameter. So del sr del b divided by del b equals to 0. So if we perform the differentiation, what do we have? uh, the 2 will come to the front, I from 1 to n, yi minus ax sub I to the power b times, okay, so b is present as a power, right, as a power of this x sub I value. So if you recall from your differential calculus course, we had a formula that looks something like this, right? So d dx of a to the power x looks something like what? A to the power x ln a, right? So we'll just apply this formula over here. So our goal is to differentiate this term, right, further. So we'll have minus, so a will remain as it is because it's acting as a constant over here. So we have this thing as our xi to the power b, right? So our xi to the power b is basically what? A to the power x, right? So we'll write x sub I to the power b times what? Ln of, so our base over here is a and the base over here is x sub I, right? So we have ln x sub I. So it doesn't take the intuition of a genius to say that, okay, the equation that we have ended up with has a long term in it, right? So it will for sure be a nonlinear equation, right? So we have ended up with two simultaneous nonlinear equations again, right, which are bivariate functions basically. So this also changes with a and b, this also changes with a and b, right? So in order to find the optimal values of a and b, we have to find the roots of these two simultaneous nonlinear equations, right? So in order to find the roots, we have to use or invoke some sort of root finding algorithm, which takes numerous iterations to converge to a good value of the parameters. So in order to avoid that hassle, we are going to, just like before, we are going to transform the data, okay? So let's see how we can do that. Okay, so let's write the equation here again. So y equals to ax to the power b, right? So in order to linearize it, we'll simply perform natural logarithm on both sides. Okay, so ln y equals ln of ax to the power b, right? Now, so here ln has a multiplication of some terms within it, right? So we can separate these terms out with the help of summation. So we know that ln y will remain as it is. So this thing becomes what? Ln a plus ln of x to the power b, right? So we can take this exponent b and bring it to the front because this is a logarithmic operation. So we can write what? Ln y equals ln a plus b times ln x, right? So now that we have ended up with this equation, we can say, okay, why not denote this using, say, z, a new variable, denote this using, say, a naught, denote this b over here with a1, and denote this last variable term with, say, a w, a new variable term, okay, a new variable symbol. So what we end up with is our linear regression equation, right? Z equals a naught times, sorry, a naught plus a1 w, where a naught is our y-intercept and a1 is the slope of the linear regression line, right? So now that we have ended up with the linear regression equation, we can use the formula that we have derived to find the value of, say, a naught and a1. And after we find the value of a naught and a1, what do we know? We know that a naught is equal to ln of a, right? So this a is the parameter of our power model, right? So we have to find the value of a. So what we can do is we can say, okay, a equals the natural exponent or the Euler's constant e to the power a naught, right? So this is one way of finding one of the parameters. And for the second parameter, we can say, okay, a1 is basically the same as b, so we can just flip it around and say, okay, the b is the same as a1, sorry. So whatever value of the slope we get for the linear regression line, we can say, okay, the value of the exponent in the power model is the same value, right? So we have ended up with both the parameters of the power model. If we plug these two values a and b into the power model, we'll end up with what? A suboptimal regression curve, okay, that fits the uh, given data point. So it will not be the best fit curve, because we know in order to find the best fit curve, we have to solve what? These two simultaneous non-linear equations, right? So let's wait for it. Okay, we have to solve these two simultaneous non-linear equations in order to find the best fit curve. But after we linearize the data, after we transform the data, whatever linear regression curve that helps us find the value of the, sorry, whatever linear regression line that helps us find the value of the a and b will give us a suboptimal power model regression curve. Okay, now let's apply it to an example and see what happens. Okay, let's go back to the slide. Okay, now that we are back to the presentation, let's continue. Okay, so this slide basically delineates how we can perform the uh, linearization of the data. So the same basic thing that we have discussed back in our bamboo paper. So we have derived these two things, right? So b equals a1 and a equals e to the power a naught, right? Where a1 and a naught are the parameters of the corresponding linear regression model, and a and b are the parameters of our original power model, right? Y equals to a times x to the power b. Okay, let's apply it to an example. So if you remember from the first part of this lecture 11, we discussed some applications of the power model, right? One of the applications was to model the what? To model the reaction rate of chemical reactions, right? So we'll do one such example. So we are given the concentrations over time of a certain chemical, which is taking part in as a reactant in a chemical reaction. So its concentration is gradually decreasing over time. So from 4 we end up with what? A concentration of 0.006 gram mole per liter, and its reaction rate will also decrease over time, right? So reaction rate is generally denoted with what? Minus R sub A, right? Because the reaction rate, this denotes that the content of the volume of mass of the reactant is gradually decreasing, okay, and the rate at which it is decreasing is also decreasing, right? So the unit for the reaction rate is gram mole per liter per second, okay, so with respect to time. Fine. So given these data points, concentrations and the reaction rates, we have to model it using the minus R times K times C to the power N. Okay, where N is the order of the reaction. So how many moles of the reactant is being used? That's the order. And K is what? K is the rate constant, as far as I recall. K was the rate constant. Okay, we found this out using some other equation for chemical. Okay, so this roughly resembles the power formula, a uh, power model equation, right? Y equals to a times x to the power b, right? So if we want to apply this equation over here, we have to use the approach for linearizing the power model regression curve, right? So let's see how we can do that. So the first thing is to what? To apply natural logarithm on both sides, right? So we end up with ln minus r equals to ln k plus n times ln c, right? That the a n at the exponent comes to the front. So we know the relations z equals ln minus r, w equals ln c, and a naught equals ln k. Now, if we find the value of a naught and a1, so the corresponding linear regression line looks something like this: z equals a naught plus a1 w. And if we apply the formula of a1 and a naught, which we derived in lecture uh, 11, right? In lecture 10, sorry. If we apply these two formula, we'll find the values of a1 and a naught respectively, right? And after we find the value of a naught and a1, we just use these two relations over here and find the corresponding values of n and k, right? N is the order of the reaction in this example, and k is the rate constant, right? Fine. So in order to find the values that we have to plug into these formulas over here, we have to construct this table, right? So we are given the values of the concentration and the reaction rates. So the first order of things is to find the value of the corresponding W, right? WIs. So we know that W can be found by performing natural logarithm on perform the natural logarithm function of the value corresponding value of Ci, right? So for 4 we have 1.38 something. So for this whole column over here, if we perform natural logarithm on this column, we'll obtain this column, right? And for the Z column, we have to perform natural logarithm on the minus R column, right? We'll find the corresponding Z column. And for the Wi times Zi, we'll have to find this column over here, and we can do so by multiplying the respective entries in these two columns, right? So if we multiply these two columns, we'll get this column. And to find the W square column, we'll just multiply this column with itself, and we'll get the W square column. And at the last row, we'll just perform an aggregate over all the preceding rows, and we'll obtain the summation of the values, right? Summation of the given 7 data point values. So after we find these values, we can simply plug them into our A1 formula over here, and we'll find the value of A1. And using the value of A1, if we plug it to the formula for A naught, we'll find the corresponding value of A naught, right? Which is what they did over here. So we'll just plug these values over here. We get the value of A1 as 0.319 something, and the value of A naught as minus 1.571 something. Okay. So now that we have found the value of a0 and a1, we can simply perform e to the power minus 1.57. We get the value of the rate constant k as 0.207, and the value of the order of the equation n as same as a sub 1, right, which is 0.319. So after we have found the value of n and k, we'll plug them into our original uh, but the rate law expression formula over here, minus r equals k times c to the power n, we'll get something like this: minus r equals 0.207 times c to the power 0.319 something. Okay, so this is the regression curve, or the power model corresponding power model regression curve for the given data points. Now, of course, since we perform data transformation, this is not the best fit power model regression curve. Okay, this is a suboptimal power model regression curve. In order to find the optimal power model, the best fit power model regression curve, we have to solve the simultaneous non-linear equations that we saw, that we derived on our Campbell paper, right? Okay, so that's the end of this non-linear regression lecture. So if you have any questions regarding this lecture, this is the largest lecture so far, right, in this course, 49 slides, right? Okay, so if you have any questions on any part of this lectures, you can contact me through email, messenger, WhatsApp, and whatnot. And you can also meet me face to face if the class reopens. Okay. Okay, fine. So if you have any questions, contact me. No worries. And yeah, so that's all from for this lecture from my side. Okay. So assalamu alaikum wa rahmatullahi wa barakatuh.